Now we're given that z is equals to exponential minus t sine theta, and we're asked to show that the two conditions here are equal. So as usual, the first thing to evaluate is the z dt, and likewise the z d theta, because z is both a function of t and theta. So that's d dt of exponential minus t sine theta, and since we are differentiating partial with respect to t, our theta is kept constant, and that is sine t with full differentiation of exponential minus t. And differentiating this, we have sine t of minus exponential minus t according to our rule of differentiation of exponential at, and we have minus exponential minus t sine theta. Now for dz d theta, we have exponential minus t sine theta, and since we are differentiating with respect, partially with respect to theta, our variable t is kept constant, d theta of sine theta, and differentiating sine theta, we will have cos theta, and thus we'll have exponential minus t cos theta. Now, having done that, let us now evaluate d square z dt squared. The square z dt squared is d dt of dz dt, and then this is simply differentiating again with respect to partial respect to t of exponential minus t sine theta, and this means that sine theta is kept constant, and we are differentiating fully of exponential minus exponential minus t, and this will give us sine theta multiplied by exponential minus t, and we have exponential minus t sine theta. Next thing to evaluate is the square z d theta squared, and that is d theta of dz d theta, and that is differentiating partially with respect to theta of exponential minus t cos theta. Therefore, our exponential minus t is kept constant, okay. Therefore, exponential minus t, let's hold on a minute, is kept constant, and then we are differentiating fully with the theta of cos theta, and this is exponential minus t, and differentiating cos theta, we have minus sine theta, that is minus exponential minus t sine theta. And in our first question, we see that the square z dt squared is equal to minus d square z d theta squared, and d square z dt squared is exponential minus t sine theta, and minus is minus here, d square z d theta squared is minus exponential minus t sine theta, and when the minus nullifies each other, we have exponential minus t sine theta to be equals to exponential minus t sine theta. So the next question which says show that d square z dt d theta is equals to d square z d theta dt. D square z dt d theta is equals to d square z d theta dt. So let's begin with d square z dt d theta, and this is equal similar to d dt of dz d theta. Now dz d theta is exponential minus t cos theta, and that is d dt of exponential minus t cos theta, and therefore our cos theta is kept constant, and we are fully differentiating exponential minus t, and this will give us cos theta multiplied by minus exponential minus t, and we will be left with minus exponential minus t cos theta. And likewise, let's do the same for d theta dt. And down this is d theta of dz dt. That is differentiating partial with respect to theta, and our dz dt, as we have seen earlier, is minus exponential minus t of sine theta. Now, since we are differentiating partial with respect to theta, our sine theta, our t is kept constant. I will differentiate fully sine theta. So therefore we have minus exponential minus t. Differentiating sine theta, we have it to give us cos theta, and this is minus exponential minus t cos theta. Now we can see that the answer here and the answer here are the same. Therefore, d square z dt d theta is equal to d square z d theta dt, and this is minus exponential minus t cos theta. Let's take one more example. Given that z is equals to x over y ln y, we should show that dz dy is equal to x d square z dy dx. Now, as usual, the first thing to evaluate is both dz dx and dz dy. So let's begin with dz dx. That's differentiating partially with respect to x of x over y in y. And when we are differentiating partially with respect to x, our y is kept constant. And that means we have 1 over y in y multiplied by the differential, full differential of x with respect to x. That will give us 1 over y in y of 1, and our answer will be 1 over y in y. Let's do the same of d dz dy. And that will be x over y of lane y. When we are differentiating partially with respect to y, our x is kept constant. That is x. And we are going to have a full differential with respect to y of lane y divided by y. Now in this case, we are going to apply quotient rule to solve the differential of lane y over y. Let's recall ourselves with the formula of quotient rule, which is v du dx minus u dv dx divided by v squared. And now that we are using y, we can change this to y. And in this case, this is our u and this is our v. So if u is equals to lane y and v is equals to y, our du dy differentiating lane y is 1 over y, and our dv dy, that is differentiating y with respect to y, is 1. Therefore we can go from here and simplify further with our quotient rule, that this will give us x multiplied by v, which is y, du dy, which is 1 over y, minus u in y, multiplied by dv dy, which is 1, divided by v squared, which is y squared. Therefore our dz dy is equals to x, and simplifying further, we left with x with 1 of minus lane y divided by y squared. This can be written as x over y squared into 1 minus lane y. Now let's go back to our question. We are asked to show that dz dy is equals to x d square z divided by dy dx. Now we are able to evaluate this, but now let us evaluate this. That is d square z dy dx. That is differentiating partially with respect to y of dz dx. Now let's go back and look for dz dx, which is here, and our answer is in y over y. That is differentiating again of lane y over y. Now this is also similar to applying quotient rule, because there is no other variable here, so that's the full differential of lane y divided by y. So with that done, we say again that this is our u and this is our v, and we repeat the same quotient rule as we've done before, and we can say that this is equal to y into 1 over y minus lane y into 1 divided by y squared, and this is equal to 1 minus lane y divided by y squared. Therefore, since we are asked to prove that dz dy is equals to x d square z dy dx, our dz dy is this x over y squared into 1 into 1 minus lane y multiplied by x is equals to x multiplied by our d square z dy dx is 1 over ln y, 1 minus ln y divided by y squared. Now we can see that in essence that these two are the same. So in our last set of videos, we have talked on first order derivatives and second order derivatives. Now in the next set of videos, we'll be talking on total differential, rate of change, and small changes.